IR spectra can be used to characterize the transition metal complexes in this experiment. You will use pentamine chloro-cobalt-3 chloride to synthesize two linkage isomers, where the chloride ligand in this complex is replaced by the NO2 ligand. Initially, NO2 replaces Cl in the octahedral complex to form the nitrito isomer, but the companion nitro isomer can be formed by heating the nitrito isomer. The nitrito isomer, which is O-bonded, can be differentiated from the nitro isomer, which is N-bonded, by comparing the infrared spectra of these two linkage isomers. Ambidentate ligands have two atoms that can form a dative bond in transition metal complexes, but because of the structure of the ligand, only one atom at a time can bond. The atom in the ambidentate ligand forming the dative bond is a Lewis base, and donates an electron pair in forming this bond with the Lewis acid. Examples of ambidentate ligands are nitrocyanidO, thiocyanidO, and selenosyanidO. The Lewis base atoms on these ligands cannot both simultaneously form dative bonds in the same metal complex, since typically these atoms are at opposite ends of the ligand. Larger ligands which are also ambidentate are shown here, with the Lewis base sites being either nitrogen, sulfur, or selenium, all of which have lone electron pairs that can be used to form dative bonds. Linkage isomers differ only in the atom that attaches an ambidentate ligand to a metal. This is a very specific type of isomer and is used primarily with transition metal complexes. The atom in an ambidentate ligand which forms the dative bond is determined by several factors, including the hard-soft characteristics of the Lewis acid and base, reaction solvent, steric and electronic factors, and kinetic and thermodynamic effects. The primary factors affecting the formation of the nitrito and nitro linkage isomers in this experiment are kinetic and thermodynamic. The overall reaction is a simple replacement of the CO ligand in the cobalt transition metal complex with the nitro ligand. Since both chloride and NO2 have a -1 charge, there is no change in the overall charge of the cobalt transition metal complex. It remains +2. The overall reaction can be broken down into several steps. After dissolving the pentamine chloro-cobalt-3 chloride in water and adding concentrated ammonia, the Cl bonded to the cobalt in the octahedral complex is replaced with a water molecule. By adjusting the pH with dilute hydrochloric acid, a proton is extracted from the bound water molecule, leaving a bonded OH ligand in the complex while forming a hydronium ion. Dinitrogen trioxide, which is very soluble in water, is formed when sodium nitrite is dissolved in water. This N2O3 then reacts with the metal complex, effectively replacing the OH ligand with the ONO ligand. The pentamine nitrito cobalt-3 complex and nitrous acid are the products formed in this last reaction. The mechanism is not a simple replacement of the OH group and the metal complex with the NO2 group. The substitution starts when one nitrogen in N2O3 forms a temporary bond to the oxygen in the bound hydroxide. At the same time, the hydrogen in the bound hydroxide forms a hydrogen bond to an oxygen at the other end of the N2O3 group. In a concerted process, the NO bond remains and the OH bond in the hydroxide group breaks. The nitrito complex is then formed along with HNO2. Note that the original oxygen in the complex is still present in the new product. The linkage isomers differ only with respect to which atom is bonded to the cobalt in the transition metal complex. In the nitrito isomer, an oxygen atom in NO2 is bonded to the cobalt. This product forms first, hence it is called the kinetics product, and either oxygen atom can form the dative bond to cobalt in the complex. The nitro isomer uses the nitrogen atom in NO2 to form the dative bond, is the more stable linkage isomer, and called the thermodynamic product, and its formation can be hastened by heating the kinetics isomer. An equilibrium is eventually reached where both products are present in any sample which originally contained only one of these linkage isomers. Starting either with the pure nitrito or pure nitro isomer, an equilibrium is eventually established where the nitro, or thermodynamic product, predominates. The dynamic equilibrium between these two forms is driven by enthalpy when converting the nitrito to the nitro complex, and by entropy when converting the nitro to the nitrito complex. This isomeric conversion does not involve another reactant. It is an intramolecular process, involving only the rearrangement of a ligand that's already attached to the cobalt transition metal complex. This conversion occurs both in solution or in the solid state, and can be hastened by heating or exposure to ultraviolet light. The equilibrium established between the nitrito and nitro linkage isomers involves a 7-coordinate cobalt intermediate, where the NO2 ligand temporarily forms 2 bonds to the cobalt before forming the companion isomer. This intermediate is transitory, and the NO2 remains affixed to the cobalt during the isomeric conversion. Here are some experimental suggestions. After all of the pentamine chlorocobalt-3 chloride has dissolved upon heating, turn off your hot plate. This will allow you to use a cooled hot plate stir later in the procedure. When neutralizing the reaction mixture, use 2 molar hydrochloric acid, not 12 molar hydrochloric acid. 12 molar is too concentrated and will prevent any product from later forming. You should magnetically stir your reaction mixture when adding the 2 molar hydrochloric acid. If the hot plate is still hot, use a clamp to suspend your beaker above the hot plate. Testing reaction mixture pH is accomplished by using a glass stirring rod to transfer a drop of the reaction mixture to a torn piece of pH paper positioned on your watch glass. Never immerse a whole strip of pH paper in your reaction mixture. Usable pH paper is yellow-orange in color. Old pH paper is usually red in color and should not be used. When taking an IR which is equipped with a small crystal platform, put a very small amount of sample on the crystal. Less solid is usually better than more solid when using solid phase ATR technique. Conversion of the nitrito to nitro isomer is best accomplished by heating in the oven. Since the nitrito isomer will convert to the nitro isomer at room temperature over a period of time, an IR of the nitrito should be taken shortly after its synthesis. The IR of the nitro isomer can be completed the week after it is prepared. IR spectra can easily distinguish between the nitrito and nitro isomers. The 1460 absorbance in the nitrito shifts to 1430 in the nitro complex. The 1065 absorbance disappears in the nitrito, and an absorbance at 1315 appears in the nitro. The nitro also shows a new absorbance at 825 nanometer, which is not present in the nitrito complex.